And good afternoon, everybody. My name is Akram Abad. I'm a researcher here at Texas A&M Transportation Institute in Raleigh. That's my camera, actually, wasn't it? Good to see you in late afternoon. I'm not going to try to make it this long. I'll realize there's some between you and your dinner or whatever you're going to do. So this is a short overview of what we do in terms of simulation activities. So I'll go over what we do and then go over all testing, all that stuff. So something about our division, analysis, design process, crash tests, and simulation, and some laser scanning there. That's where we are. We are actually in the big hangar. If you ever been to Raleigh, that's where we are there. We have this big old World War II hangar that we do a lot of vehicle preparation. And we have a big staff to do a lot of construction, mechanical, and last year we logged over 100.
Akram,
yes.
Probably want to hide your bar, the menu bar at the top. It seems blocking the screen on my end. Might be doing something to other.
Oh, my bar. This is the transcript.
Yeah, it seems it's blocking the. Yeah, there's another one on the top. Yeah.
I don't know how you hide this one though.
You can drag it around probably. You can try.
Okay. Officially, we don't have Zoom, so
okay,
I'm new to
good.
Zoom. We use Teams. Okay, thank you for your tips. That's our division, and as you, Gian, mentioned, like we do crash testing, but a lot of roadside safety. A lot of credit go to HPRC. We have a lot of hours with them in terms of like using this analysis on their facility. So I'll go that's about proof ground, and credit go to everybody really. I'm just presenting some of the work. So let's get started. This is it's kind of sample crash test. Did you hear it or do you see it? But that's very much a T-wheeler going in the bridge pier. That bridge pier actually is not rigid. It looks rigid, but it's actually flexible. It's very stiff that you don't see moving, but at the very end here, there are these two load sensors, each 1 million pounds each. So we get this instrumentation from that, trying to find what the load will be on a bridge pier from a heavy vehicle that's running around there. Back to safety really overall, and I don't have 2021, I'm looking for that, but the US have 38,000, more than 38,000 fatalities, just 2020. And that's more than 36,000, of course, that's 2019. So even though during pandemic, fatality increased, and the same thing for Texas. You have 3,800 to 3,000 from 3,600. So that's a serious problem. Overall, from the 75, you can see there's a trend in terms of million vehicle mile traveled. That's kind of a sort of a normalizer. So it's going down, but we're very much not going down that fast over the last 10 years or so. Having that, so how we do that, there are 4 E's from Federal Highway: education, engineering, enforcement, and then the emergency service really. Everything about autonomous vehicle, all that has to do with education, the driver. So that's the portion of it that control the driver. But what happened if vehicle end up, errant on the roadway? So that's where the engineering comes in. Well, you have the mechanical part of the vehicle, but then the road, and that's where we focus on how to make the road safer. And on focus here is the roadside safety devices. So these are to shield, contain, redirect the vehicle away from hazard. And they're fixed object, non-traversable object, and many other features you've seen on the road. You probably don't know they were tested and have some safety criteria, but they are cable medium barrier down here. You have concrete, you have W-beam, you have a bridge rail, straight bridge rail, and also you have crash cushion. You've seen several types of crash cushions. Some of these are really commercials, and some that are public domain. And these standards were evolved over the years, and many of these standards has to kind of do with the fleet. Fleet change, we have a smaller vehicle, kind of wide, big station wagon. Now we have SUVs, and in the 90s, more of a big kind of flurry of SUVs. And now we have more of a different type of vehicle, like compact SUV, medium-sized SUV, all that. So how the vehicle type, how the vehicle impact in terms of velocity and impact angle. And all that we need to kind of figure out to put in our crash test. And then also need to figure out on the device what's going to do. There are 3 major kind of heading of criteria, but then you have a lot of sub-criteria. I'm just have a few examples. Big one, no-brainer, structural adequacy. You don't want the device to just break in and the vehicle breach through it. And then you have the occupant risk. When you have to make sure the impact is not severe on the driver or occupants, all of them. And there's a criteria on the occupant impact velocity, OIV. That's if the inside occupant hit the inside of the vehicle, that'll be less than 9.1 meter per second, preferably 12.2 is the limit. And for ride down after the occupant kind of engage the vehicle and they're one piece, the deceleration should average on 10 millisecond average less than 20.49 G and preferably less than 15 G. So that's the G force. And then of course, post impact, what the vehicle is going to do, you don't want it to get out and then hit another vehicle under it. So that's an old footage crash testing then. And you can see the vehicle putting down a track. And you can see all the engineers and they dressed very nice for occasion with hat, vest and tie. But you have propulsion systems for going down the hill and tracking system, actually the tracks. And now very much we have more like, tow vehicles, cable. We have a lot of high-speed camera as well as the propulsion systems. We're gonna through a cable control with the speed of that, and then you can see the dummy on the passenger side here there. So guideline, we just go over the guideline. These are kind of like the stance from one page, 1962, and then just stop propagating. And this 1993 was actually mandated by Congress. And 2009 came a new one called MASH, Manual for Assessing Safety Hardware. Second edition came 2016, very much have some changes there. So what we do is we kind of try to bracket the vehicle. We cannot test every vehicle out there, but you have tried the worst case and more representative the fleet based on sales, all that. So you go with the small passenger vehicle. This is very much now a Nissan Versa, Toyota Yaris, and then this is Kia Rio. The mid-size, very much this is just for staging, so I don't have it here, but then you go pickup truck, represent light truck, SUVs. So you have the Dodge, a Ford F-150, and then the GMC and Chevy. A quad door has to be there. And then go to single unit truck, 10,000 kilograms. So that's more like your delivery, neighborhood delivery. And then, a grocery delivery kind of type vehicle there. You go up 18-wheelers. So that's about 80,000 pounds, 36,000 kilogram. So that's tractor van trailer, 18-wheeler there. And then the highest test level 5 is test level 6, is the tanker, same mass, but now you have a tanker. And that one, because you have some slushing there. So it's a different test than the 18-wheeler van trailer. So these are the heavy vehicle there. To have that, then you have different kind of test configuration. With 25 degrees are for the smaller vehicle. So you can see the small car, pickup truck, and these are on the barrier direction. If the speed is what they call TL3, you can go lower speed. Let's say if you're going to neighborhoods, where you have devices, and then you go to 45 miles an hour devices there. When you go to a single unit truck, you have to go a little bit shallower angle because really they don't converge at a very high. So these come from statistic and a lot of crash data analysis. And then you have the encroachment speed. So 15 degrees will be for single unit truck, 18-wheelers, and then tanker truck. So I'm going to show some tests. I'm going to go a little bit more on the simulation later on. So this is, for example, a bridge rail. And we have an 18-wheeler here. And then bridge rail is basically a half concrete parapet. And then you have a steel rail on top. And that's how we tested. We managed to kind of have certain towing system as well as a propulsion on it. And it did kind of redirect, which is very, very what you want there. And then this is the camera. This is a GoPro right on the rail. So that's an extra camera there. It's very kind of give you a view of it. And you can see when the impact happens. Okay, if you're not dizzy now, but the camera is doing fine. But we just knocked the camera off with the side impact, basically the back impact. So you have three impact, the curse of the vehicle, then the real tandem of the tractor. So that's here second, and the third right now. And that just get the camera out. So with that's like very extensive operation. It's needed, required, but can we do better? And that's where simulation comes in place. So we go on different kind of major step, but this case, like you have what they want from the agency, what kind of device they want to put there. You do concept development, 3D modeling, and then you do material testing and eventual simulation and crash testing. So some of these are really kind of your basic finite element deal. You have to look at that, but also do like what's called discrete element. So you start kind of building everything from the ground up and try to satisfy Newton's second law or the equation, balance of momentum really on the finite element there. So this is an example here of what we used simulation in there. Basically, you have a bridge, which you can see that the bridge kind of steel bridge, but then as you approach to it, you remember you go up to the bridge, let's say it's an overpass. And as you go up, actually what you are going up, you're going above a soil, just plain soil. And here you have what you call mechanical MSE, mechanical stabilized earth. And these are just panels, like very thin panel. And you still want to have a barrier on top of that. So you can put barrier on top of like a steel bridge, but how are you going to put the barrier here? Because this is really a flexible system that the barrier is going to be on top. So a lot of that happen is that we reinforce the soil to keep the soil stabilized. So these are still within the soil model. Then you have the mass of soil, and then you have the panel, but you can see this this piece, that kind of trapezoid cross section, that's really a big, massive concrete to stabilize the barrier. So it stays on top of the soil. And then we add kind of reinforced now. So that took a while to model there, but basically you end up having the barrier attached to that piece of concrete. So you can see that's an 18-wheeler kind of impact. So this is quite a large system here. You have 30 foot times 6, so an 80 feet worth of construction. So we end up also putting on construction and try to test that. And it did its job. Redirect, that's the GoPro on the side, on the other side. So that's a very nice success story. The other one is basically where we have to look at a very sharp turn called like short radius. So how do you capture a vehicle where you have concave, that doesn't allow you for tensile capacity? Because when you have an arc, you cannot have tensile if you go from the outside. And one way to do that is really to add a mass to reduce the vehicle velocity at controllable rate, so we don't have any. Let's go up a little bit. We don't have any kind of tendency for it to overwrite it. And it did a job, and then once the job is, then the rails start engaging the front of the vehicle, and it captures. So simulation before, testing after here, and that's a very nice prediction here for a very large system with a lot of details, including discrete element simulation. So the mass, of course, we cannot do the particle that's just huge amount, insane amount of sand, but you can do certain representative kind of, sort of reduced model, I guess the order here, of the sand. So you have, instead of, millions and millions of sand particles, you have just 20,000 in a bucket. Moving forward, this is a big, large work in Illinois. This is a sound wall. So sometimes you have highways going over residential area, but you need to kind of reduce the sound going there. So they want to have a sound wall. The thing with the sound wall, they are really flimsy in terms of impact. So how close can you have it without having to worry about doing a bigger structure to go overhang? That's very costly and problemsome. So that's where we're trying to kind of find out how close can we put it without the train leaning on it, but having a barrier that's long enough to reduce the amount of lean on it. So that's modeled all the way from the ground up as well. Reinforcement, steel, concrete, the deck, the barrier, as well as the sound wall and the steel bar. So there are two designs that were tested, and you can see some of this like we're showing you from the field side. And basically we're saying is it's going to be close to it, but it's not going to be, even if it's going to come close, probably not going to cause any issue with the sound wall itself, because this barrier length is enough to kind of contain the trailer there instead of leaning too much. So, and that's also, we get some prediction on the joint. We have some inside, and we did measure that. I don't have the measured with me on the rebar, how much they're going to withstand the of stresses in case things are going to be really, taking care of the force being imposed on it, or are they like, at the limit? So they seem to be a lot of, good condition, healthy condition here. And then you have some damage. You expect some damage, but not catastrophic damage. So with that, we kind of simulation on the left, that's predict, and that's the testing. And eventually to redirect, it's come really close to it, but didn't affect the sound wall, which is really a success. That's kind of the point the sponsor want to look at. And that's some damage prediction before and after. Overall, the global area is where we expected. That kind of showed us on the system. Finally, I'm going to go over scanning a little bit. I'm probably short on time, but a lot of time, well, how you get the models. So sometimes they're available public domain, but sometimes we have to kind of build them from the ground up. And that's where like data with scanning. So we have localized as well as a large scale scanner. So we can go on some component there. So we use that to kind of scan, get material testing, and then build the geometry. So that's for a single unit truck. We get all the global measurement, weight, masses, and then center of gravity. We have this kind of vehicle to get where the CG located. And then we start doing some alignment, what they call target auto match. Basically, we put some spheres. So when the camera go around the laser, we can have a reference which on a frame, became close to each other. And with that, basically we use billet balls, and they're very kind of, inexpensive. And then you have to kind of put a paint to dull them because the laser doesn't like a shiny object, and put a threaded bolt there. And then we do a measurement on them. So that's 57.14 millimeter. And with that, when we put them on the vehicle, we can know where they are. So these are scanned, assembled based on that alignment. And you can see the vehicle very much kind of came into life with that. So of course, with then like onion, you just take out the outside shell, go back scanning the parts inside till you get all the part. You mesh them, you can see the point cloud, you go triangulate mesh, and then you have a spline, then you get an actual finite element. And since it's physics, of course, we have to have material property. And so we have a lot of coupon tested. And then you build a model from the ground up based on the scanning. And this is really a nice mesh of a single unit truck. And then we have an actual test. This is for security, actually, not roadside safety, but like kind of somebody heading on in a facility. So that's the same pier that I showed you earlier on, but now we have an attachment to it. And this is really the model in there. So it's a little bit work in progress and trying to capture frame on that, but overall, it's going to give you a good global correlation with it, including the damage to the front and the behavior of the cab. So that's all really. We work with a lot of data from signals in the vehicle. During tests, we try to make sure they don't get destroyed. And so they have certain location there. And we have the yaw angle, all the Eulerian angle of the rate sensors of the vehicle. We know the vehicle path overall, and sample on the CG accelerometer, X, Y, and Z triaxial accelerometer. And then as we need, we might do a dummy in there if needed there. That's it. And if you have any question, let me know. Hopefully you have a good.
Thank you so much. And it's great. I saw many new videos I didn't saw before because I subscribed to the channel. I didn't see new videos, But some of those were not posted, right, to YouTube channel yet.
Yeah, we're YouTube says 45 years, and now we're almost 58 years of testing. So we have good 10 years worth of testing that are not out there. We're trying to, we just didn't have time and resource to put together, but we work on it. It's been a project ongoing there. So you're absolutely right.
Great. It's wonderful work, both physically but also digitally. The simulation is fabulous. And any other questions from our audience? Anyone?
Well, that's it.
I hope Andrew is here. I think he might ask you some question about how you guys did the modeling. It's that's more or less like what his team is trying to do. Is doing this piecewise modeling and then put those things together. And I'd like it's kind of like your approach, but you are doing things for the sake of the mesh, right? You're trying to build up the mesh based on each component.
Yeah, I want to have a physical base model, so I can probe the model for for simulation as well as see what's the strength of the model, all that. So there's a physical aspect to it, physics, how strong the actual system is. And then we damage stuff. So that's kind of like the other thing about where you put the sensors. You can see that camera was doing fine, but it get knocked out, So that's a big deal for a camera, Okay, well, thank you very much.